Hello, this is section 4.2 area. So this section, we begin with introducing a concise notation for sum. So this notation is called the sigma notation because it's used the upper case Greek letter sigma written as these symbols. And then sigma notation is going to be the sum of the n terms from the a sub 1 to the a sub n is written as a sigma and then n equal to I equal to 1 to up to n and the a sub I, this is general form, and then we are adding all the way to up to the a sub 1 to a sub n, where the I is an index and in the index of the summation, and the a sub I is the ith term of the sum and the upper and lower bounds of the summation and n1. So property of the summations, the property of summation shown below here can be derived using the associative and cumulative properties of the addition and distributive property of the addition over multiplication. Excuse me. In the first property, k is a constant, so k that I use here is so you can pull it out, and you can just leave the sequences to add it up. And also the addition and subtraction works for that case too. So summation formula, okay, so when you have just a constant added 1 to the n terms, you can just write the how many terms of c, and then the n times c works, okay? And then number 2, when you have I, which is I changed from the 1, 2, 3, 4, 5 all the way to n, and then this is a formula that you can use too. And also when you have I square, and then it's going to be the from 1 to n, this is the formula that we can use. And then sigma I equal to 1 to n iq, and this is also the formula that we can use to find the sum easily too. So let's talk about the sum we have here. So which is, this is not that many terms, so instead of using the summation formulas, I think I'm just going to find the sum, okay? So in this case means this. We're adding the 1, 2, 3, 4, 5 terms together. So I is starting with a 1, which means you use the 1 for I. That's a 1. Then I becomes 2, which is 2 times 2 plus 1. Now I equal to 3, which is 2 times 3 plus 1. Now I equal to 4, which is 2 times 4 plus 1. Now I equal to 5, which is 2 times 5 plus 1. Now you gotta simplify. So 2 times 1, 2 plus 1 is 3. 4 plus 1, 5. 7. 8 plus 1, 9. And 10 plus 1 is 11. So when you're adding it up, which is, it becomes 35. Okay, so without the formulas, we can find the sum. All right, let's do the second one. So second one, the k times k minus 2. Of course, you can distribute the k and say k squared minus 2k, and then you can start plugging k equal to 3. So we need to start with the k equal to 3. So that means what? 3 times 3 minus 2 plus, now k equal to 4. 4 times 4 minus 2. K equal to 5. 5 times 5 minus 2. Now last term, k equal to 6, which is 6 times 6 minus 2. Simplify. So 3 minus 1 and 3. 4 minus 2 times 4, 8. 5 minus 3 times 5 is 15. And then 4 times 6, 24. So when you do this, you got I think this becomes a 50. All right, so that's how you find the sum. All right, next page. Now use the sigma notation to write the sum. So we are using what kind of sigma notation we can use here. So sigma notation means we bring out the sigma. And then I want to say I is equal to. So you have to kind of check that what is the staying, what is the changing. So as you notice, all the 1 stays the same, right? So it's going to be something 1 over. And also in denominator, and then you see the 3 staying. So it's going to be something 3 times. And then what is the changing? Actually, the number in the parenthesis, which is going to become 1, 2, 3, 9, isn't it? So it's going to be that numbers are changing by 1. So I want to say I here. So 3i. And then it's from the 1 through the 9. So I equal to 1 to 9. And then if you don't want a parenthesis, it's going to be just I equal to 1 through 9, and then 1 over 3i. So that's it. That's the sigma notation. And also the second one, same thing too. So sigma I equal to, and then I know the fractions, so I see that the 5 on the top, right? There's all 5 on the top. Yeah, so there's a 5 on the top. And then in the denominator, the first number stays as a 1, right? So something 1 plus. And then denominator as also has the start with the 1, 2, 3 all the way to 15, right? So which means this starting the as I here, and then from the 1 to 15. So that's all. And for the number 3, you have to check it out. So in here, I can see that there's a 1 over n, 1 over n stays the same, and the square root stays the same, and then 1 minus stays the same, and then only the changing is 0 and up to the n minus 1, and then power stays the same and denominator stays. So something doesn't change, you just need to keep it as a formula. So formula I equal to, and then I see that 1 over n stays, square root of 1 minus something squared stays over n. So only thing is changing is gonna be the numerator of this place. So in order to find that, okay, so start from the 0, which means there's a 0, 1, 2, 3. That's what we expected. So I can just say I here. And then the I starting from this time is a 0. So I'm going to put the 0 here. And then all the way to the last number you see is n minus 1. So I put the n minus 1 on the top as an upper bound, okay? And that's all. And then use the property of the summation of the theorem 2 to evaluate the sum. So now I'm going to use the summation notations, okay? So which is the formula that I just showed it to you right here in the 4.2. So okay? So in that case, all right, so let me pull it out. So this is the difference of the two terms. So I can write as sigma I equal to 1 to 15 of 2i minus sigma I equal to 1 to 15 to 3. And also I can pull it out as 2 times of sigma, because 2 is like a k, which is a scalar. And then I minus sigma I equal to 1 to 15 of 3. Now I can use a formula. So 2 times up. So formula for this one is going to be the n times n plus 1 over 2. So n is 15 times 15 plus 1 over 2. So this is how we converted it, okay, to that. Minus, and then 3 is a constant, so you just need to multiply 3 to the n 15. That's n. So 3 times c times n, right? And then when you simplify, you get 195. All right, for the second one. So for the second one, which is I'm gonna actually distribute the I to get sigma I equal to 1 to 10 of I cubed plus I. And then I can make this I equal to 1 to 10 I cubed plus sigma I equal to 1 to 10 to I. And then formula to the I cube is n squared times n plus 1 square over 4. So I'm using as n is a 10 square and 10 plus 1 square over 4. And as I is n times n plus 1 and then divide by 2. And then when you compute that, it'll be 3080. All right? Okay, so let's look at the next page. Now, we're going to find the area of the polygon, okay? So area in Euclidean geometry, the simplest type of plane region is rectangle. So although the people often say that the formula for the area of the rectangle is base times the height, which is the length and width, is actually more proper to say that it is the definition of the area of the rectangle. From this definition, you can develop the formula for the area for many other plane region. So for example, to determine the area of the triangle, you can form up the rectangle. See, so you only see the triangle, but make the rectangle and then multiply base times height and then divide by 2, which is going to be the area of this the triangle. All right, and then once you know how to find the area of the triangle, you can determine the area of any polygon by subdividing the polygon into the triangular region and show as this. So parallelogram, you can just drop the dashed line to make a 2 triangle. And for the hexagon, you make a 6 triangle. And the polygon, you make this one has the 3 triangles. So you can find the area for this one. So finding an area of the region other than the polygon is more difficult. So ancient Greeks were able to determine the formula for the area of the some general regions, principally those bounded by conics by the exhaustion method. So clearly the description of this method was given by the Archimedes. Essentially, the method is a limiting process and in which the area squeezed between the two polygons. One we can get the inscribe and the other one is the circumscribe about the region. So let's take a look at the next page. So next page, for instance, for the figure 4.7, which is the picture below, the area of the circular, which is this one, okay? So this is a figure 4.7. The circular region is approximately by the end side of the inscribed polygon. So end side the circumscribed polygon. So the outside, the inside was this one is the inscribed polygon, and then the circumscribed is the outside ones. Okay, so in order to find the area of the circle, I mean, make a very small of the triangle, and then we can figure out the area of the circle. So for each value of the n, the area of the inscribed polygon is less than the area of the circle. Oh, yeah, right. So I think I put it, yeah. And then the area of the circumscribed polygon is greater than the area of the circle. So more than n increases, the area of the both polygon becomes better and better, and the approximation of the area of the circle. Okay. So let's try this of the problem here. So example 4. The use of 5 rectangles in figure 4.8, A and B, and to find the 2 approximations of the area of the region, and lying between the graph of the f of x negative x squared plus 5 and the x-axis between the x equal to 0 to 2. So these are exactly the same, but one is we are having the try the area of the circumscribe, and then the other one is the inscribe. All right, so let's see here. So A, so this time the first one, okay, if I get the first one, so this time we are using the right endpoint. Okay, we're using the right endpoints to get here of the rectangle. So right endpoints actually give us the height. Okay, all right, so let's do this. So the right endpoint of the 5 interval, which is the interval is 1, 2, 3, 4, 5, gonna be 2/5 of I. Okay, so each one is interval of 2/5. But increase by I, right? I equal to 1, 2/5, 2, 4/5, 3, 6/5, like that, okay? And then, which is where I equal to 1 and 2 and 3, 4, 5. And then the width of each rectangle is 2/5, right? And then also height of each rectangle you can find it from the, so can be obtained by evaluating function at the right endpoint. Of each interval. So but each interval is from the first interval is 0 to 2/5, as you notice, right? Talking about this. And then the second interval is going to be from the 2/5 to the 4/5. And then 4/5 to the 6/5. And then 6/5 to the 8/5. Okay. And then 8/5 to the 10/5. So in order to get a sum of the area, the sum of the areas of the 5 rectangles is, okay, so we're going to get I equal to 1 to 5. And then the base, the half of, it's going to be 5, half of 2I over 5 times 2/5. Because when you actually x that you plug it in, which is that's the place, okay? So this is a 2/5 by, so which is this whole thing makes the height of the rectangle, and this is actually makes the width. So length time height, which is a width time height, will becomes the area of the rectangle. So when you do that, and this is actually the same as sigma I equal to 1 to 5 of, and then you plug it in the 2I over 5 into the function of negative x squared plus 5. So if you do that, it'll be 2I over 5 squared plus 5, which is that's the height, and then multiply by width. And then if you simplify this, you get the 162 over 25, and then it's about 6.48. Okay, so that's the area of the actually the square inside of the kind of curve. So because of each 5 rectangle lies inside of the parabolic region, you can conclude that the area of the parabolic region is greater than, and then 6.48. So which means the area of the parabolic region. So they're talking about the whole thing here, right? Because that's the area of this is the 5 of the rectangle, but area of the under that is going to be greater than, and 6.48. Okay, alrighty. Now I'm gonna use the left end point. So I'm using this time the left end point here, left point of the rectangle. Okay, so if you use a left point, so the left end point of the 5 intervals are, this time is actually the 2 over 5, of course, and then it's going to be I minus 1 this time. So instead of start with the I, and this is a 0, so I minus 1, which is the left points where I equal to 1, 2, 3, 4, 5. So the width of each rectangle is the same as what we have. And then, but the height of each rectangle can be obtained by evaluating function at the left endpoints of each interval. So the sum is same thing as this. So we use I equal to 1 to 5 of f of, but this time we are using the 2 over 5 I minus 1 as the height, and then multiply by 2/5 as a width. Okay, so same thing. So this is going to be the height, and this is a width. So if you do that, it becomes a sigma I equal to 1 to 5 of, you can just put it as negative of 2/5 of I minus 1 square plus 5 times by 2 over 5. And then you will get as about 202 over 25. So it's about 8.08. So because the parabolic region lies within the union of the 5 rectangle region, so that you can conclude that the area, we can conclude that the area of the parabolic region is less than 8.08. So because the area that we find is about the area of the rectangle, so but we are not using there's cutoff, which is the parabolic area will be the less than the area we found. So what we can conclude it, the area of the region has to be less than 8.08, but also greater than 6.48. So we just do this ways, okay? All right, then let's look at the next page. So find the area by the limit definition. So is there another way so we can find it? So consider the plane region bounded above by the graph of the non-negative continuous function y equal to f of x as shown in the figure 4.9. The region is bounded below by x-axis and the left and the right boundary of the region vertical lines x equal to a and x equal to b. So they're talking about those, okay? So this, and also boundary by the x-axis, okay? And then it's close, actually this is the area we're looking at, right? All right, to approximate the area of the region, begin by the subdividing the interval a to b into n subintervals. Each of the width gonna be this, okay? So when you try to get the one of the square of the interval, which is this is a kind of width, and then this is what we're gonna get. That's the change in x, okay? I just shown as a figure of this one. And then the endpoint at the intervals are, so you're starting from the a plus of the interval. So start from the 0 and 1 times the interval, 2 times, and that. So that gives us actually, so at the end, you'll be the n times the change in x. Because the f is a continuous, the extreme value theorem guarantees the existence of the minimum and maximum value of f of x in each subinterval. So f of mi is the minimum value of the subinterval, and then f of uppercase mi is the maximum value of the ith intervals. All right, let's look at the next page. So next, define the subscribed rectangle lying inside of ith subregion, and then circumscribe rectangle extending the outside the ith subregion. So the height of the ith inscribed rectangle is f of mi, and then height of the ith circumscribed rectangle is going to be f of mi. So for each of I, the area of the inscribed rectangle is less than or equal to the area of the circumscribed rectangle. So we can kind of think about this. So this is kind of think about that. So upper and lower sum, so the sum of the area of the inscribed rectangle is called the lower sum. Then sum of the area of the circumscribed rectangle is called the upper sum. So yeah, we can get the sum as that. And then the figure 4.11 said that you can see that the lower sum S of n is less than or equal to the upper sum of Sn. So yeah, so this is could be that get. And then if you get a narrow, almost like a stick of the rectangle, and then this almost come out the same. So the area that we're looking for in the middle will be the area will be of the inscribed rectangle, and then similar to the area of the circumscribed rectangle. All right, so let's do 5 to see how we do this. Okay, so find the upper lower sum for the region bounded by the graph of f of x equal to x squared, and the x-axis between the 0 to x equal to 0 and x equal to 2. So I have exactly the same, but I'm going to find out the inscribed rectangle, which is its size less than the area under the curve. But circumscribed rectangle will be the bigger than the area under the curve. So because the function is increasing on the interval to 0 to 2, as you noticed, the minimum value of each subinterval occur at the left-hand point, and then the maximum value occurs at the right-hand points. So I want to do the left-hand point first, okay? So left-hand point. Left-hand points. So which is this one? So left-hand one point is this one. So this one. So let me get the, actually, the left-hand point is here. Okay. So I want to put that as a mi. As so this is going to be a 0 plus. So a plus a is a 0. And then starting from the 0. So I think I can, oh yeah, so sorry, yeah, well, I think I should get from here. And then 0 plus of the, it's going to be I minus 1. And then 2 over n, because the delta x is going to be 2 minus 0 over n, right? And then, which is when you simplify, you get the 2 times I minus 1 over n, okay? So if you're using the left endpoints, the lower sum is, which is f of mi times delta x. So and then mi was the same as that we found here, which is a 2i minus 1 over n. And then also the width gonna be the 2 over n. So now when you are plug into the function, which is x squared, so it's going to be sigma I equal to 1 to n, and then 2n go 2 times I minus 1 over n should come into the x squared times what? 2 over n. Now we just need to simplify this, okay? So in order to simplify this, we got the sigma I equal to 1 to n of, and then when you square this, so 4 times of I squared minus 2i plus 1 over n squared of the 2 over n. And then it becomes I equal to 1 to n of, and then 4 times 2 is 8 over n cubed of I squared minus 2i plus 1. And then if I use the formula, I can pull out the 8 over n cubed, and then I get the sigma I equal to 1 to n of I squared minus 2 times sigma I equal to 1 to n I plus sigma I equal to 1 to n times 1. And then I get the 8 over n cubed, and then the formula for the I squared, I'm getting n times n plus 1 times 2n plus 1 over 6 minus 2 times, and the formula for the sigma I equal to 1 to I is the same as n times n plus 1 over 2, and then 1 times n is n. And then if you simplify further, you get the 4 over 3n cubed of 2n cubed minus 3n squared plus n And then if you multiply by the 4 third, 3n cube as a distribute, you got the 8 third minus 4 over n plus 4 over 3n squared. So this is what you get. All right, let's see what we're going to get using the circumscribed rectangle. Okay, so this is what I'm using the right hand point. Which is I'm using the point this one to this 3, 4, 5. Okay. So this time I'm using the uppercase sub m I, which is going to be a plus I times 2 over n, which is 2I over n. So we are using the right endpoints this time. So now we are getting an upper sum. So S of n, uppercase, and then sigma I equal to 1 to n of f of mi of delta x. And then sigma I equal to 1 to n of f of mi is 2I over n plus delta times delta x. And then if you plug it in to the function x squared, you get the 2I over n squared plus delta times, the delta x, we know this. So you can put that as, so 2 over n. This becomes I equal to 1 to n of 8 over n cube of I squared. And then 8 over n cube of, and then if you pull out the formula for the I squared with the sigma, you get the n of n plus 1 times 2n plus 1 over 6. And then you'll get 4 over 3n cube of 2n cubed plus 3n squared plus n. And then you'll get the 8 third plus 4 over n, and then plus 4 over 3 n squared. Okay, so that's actually the area. Alright, so I divide this too. Alrighty, so we'll get a little different form. Okay, and then next one. The next theorem shows that the equivalence of the limits, which is n approach to infinity, of the upper and lower sum is not mere coincidence. So it is true for all the functions that are continuous and non-negative on the closed interval a to b. So theorem 4.3, the limits of the lower and upper sum, if the after continuous and non-negative on the interval a and b, the limit as n goes infinity, that both the lower upper sum exist and are equal to each other. That is, so we got this. So this is actually the formula that we got here. Okay, so which is come out as this, and then sum is this one. So where the delta x going to be b minus n over n, f of mi and f of mi are minimum and maximum value of the f in the ith subinterval. In theorem 4.3, the sum limit is obtained for the both minimum value of f of mi and the maximum value of f of mi. So it is a follow from the squeeze theorem, which is we learned that in the theorem 1.8. And then choice was whenever the two function between, and then the two function limit goes the same. And then also the middle function goes the limit to the L. So this means that you're free to choose the arbitrary x value in the ith interval as shown the definition of the area of the region in the plane. Alright, so the next problem. So definitions of the area of the region in the plane. So that after continuous and the negative on the interval a and b, the area under the region bound by the graph of function, and also from the a to b. So we try to look for those. So area, find that is the limit n goes infinity, and of the function we have. So this is a height and this is a width, and where the x of I minus 1 less than equal to c sub I, that x of I, which is that's actually the width that we can find it. All right, so find the area, the regions, the region bounded by the graph of f of x cubed. The axis and the vertical line is x equal to 0 to 1, and show that to here. So area, the region is bound by the, we have that already. Alrighty, so begin with noting that the function is continuous and non-negative on the intervals of the 0, 1, as you notice. and the next that the partition and interval 0 to 1 into the subinterval. So we know that the delta x will be the 1 over n. Okay, because that's the n number, so 1 minus 0 over n. Okay, so according to the definition of the area, you can choose any x value in the ith interval. So this time, I'm using the right end this time. So the right end point, because they're using the right end here, right? So right end. And point is, I want to say CI equal to 1 over n, which is convenient to use. So area. That is limit n goes to infinity, which is sigma I equal to 1 to n of f of ci of delta x. And then the limit n approaches to infinity, sigma I equal to 1 to n. And then ci is the same as 1 over n. And times delta x is 1 over n in the right hand points, okay? And then equal to limit n goes infinity and sigma I equal to 1 n, and then you plug in 1 over n into the cube and then times 1 over n. Oh, sorry, it's I. What am I talking about? I over n. Okay, so I. All right, and then you get the limit n approaches infinity, and then you can see there's a 1 over n fourth, and then it becomes I equal to 1 to n and I cube. And then if you use a formula, 1 over n to the 4, and then you got the formula what the I cube is, and square of n plus 1 square over 4. And then when you simplify, you got the 1 over 4 plus 1 over 2n plus 1 over 4n squared. But since the n goes to infinity, so this goes to 0, and then answer is, you want to say 1/4. So we can say the area of the curve under the curve is about 1/4. Okay, all right, that's all. Okay, alrighty. So which is in here I want to say right end point is CI is going to be I over n. Okay, alrighty. Okay, that's all. Thank you for listening.